In our first exercise, we would like to determine the angle between vectors p and f. This is the identical figure from the first of our exercises in section 2.3, so you may want to go back and look at your results from that problem and make a note of the three-dimensional vector representation of p and f. Pause the video now, and when you're ready to see one solution, resume play. From our earlier exercise, we have the three-dimensional representation shown here. We'd like to find the angle between these two vectors, p and f, and we should first just make a note that if we were to try to do this visually by somehow identifying the plane formed by p and f from this figure, that would be extremely difficult. What we do know from the dot product is that we can find the angle easily between them, if we call that angle theta, by writing cosine theta equals p dot f over the product of the magnitudes p and f. Since the dot product is just the sum of the products of the x, y, and z components, the numerator becomes minus 1.327 times 2.121 plus 0.766 times 1.5 plus 1.286 times 1.5. The result is that the right-hand side is equal to a small number, 0.0439, which tells us that theta actually is pretty close to 90 degrees, and if we take the arc cosine, we end up with a value of 87.5 degrees. Here we have a second problem involving a whistle made of square tube with a notch cut in its edge, and we'd like to determine the dimensions d and theta for the baffle shown. Pause the video here to try to solve for the dimensions d and theta, and resume playing when you are ready to see a solution. To begin, I'm going to just identify some points on this baffle. I'm going to call this vertex O, this vertex A, and this vertex B. And we'll just make a note here that ROA lies in the XZ plane, and that ROB lies in the YZ plane. For that reason, identifying the magnitude d is quite straightforward, because we have with either one of these, and it's probably easier to see it here, we've got a right triangle. So we can say on this basis that d sine of 60 degrees is equal to 5 centimeters, and that in turn means that d is 5 centimeters over sine of 60 degrees, which turns out to be equal to 5.774 centimeters. Now we can represent both ROA and ROB as magnitude distance d on a unit vector that points in an appropriate direction. Since ROA and ROB both lie in well-defined planes, we know that we can define a two-dimensional unit vector in terms of the cosines and sines of the angles made with a particular axis. So for instance, we can see that we could represent ROA as the distance d times cosine of 60 degrees in I plus sine of 60 degrees in K, and we could write that further as d times 1/2 I plus root 3 over 2k. This becomes the unit vector that points in the direction of OA. For ROB, we have something similar. We have the distance d on cosine of 60 degrees in J plus sine of 60 degrees in K, or d on a unit vector 1/2 J plus root 3 over 2K, and this becomes the unit vector in the direction of OB. Now, one of the nice things about unit vectors in a problem like this is that they each have magnitude 1, so we can find cosine of theta, the angle between these two vectors, as UOA dot UOB divided by the magnitude of each of those vectors, which is just 1. So it's what we have is that theta is the arc cosine of UOA dot UOB. And notice that the only thing that's common between those two unit vectors is a k component. So the numerator here will simply be root 3 over 2 squared, or 3/4. And theta then is just the arc cosine of 3 over 4. And that number turns out to be equal to 41.4 degrees. Finally, we have a problem involving a gear shift lever AB. We're told that if the component of F perpendicular to the gear shift lever must be 5 newtons to shift gears, that we need to determine the magnitude F of the force. So here we're given a relative position vector as indicated by R that indicates the line of action of the lever, and we're given a representation for the force vector F, which includes an unknown magnitude and a known orientation through a unit vector, and we need to define the magnitude of F so that the perpendicular component to the line of action of R is 5 newtons. Pause the video now and try this problem yourself. When you're ready, resume play to see a solution. In a problem like this, where we have a well-defined line of action and we want to resolve a vector parallel and perpendicular to that line of action, it's easiest to begin with a dot product to find the parallel component and then back the perpendicular component out of the relationship between the resultant vector F and its parallel and perpendicular components. So one of the things we're going to need to do to start this problem is to define a unit vector along the lever AB. R is given in the problem statement, and we'll just note that we can find the magnitude of R as the square root of the sum of the squares of these components, and that turns out to be 15 millimeters. So we can write R as (15 millimeters) on a unit vector that points in the direction of R, and that unit vector is simply minus 1/3 I plus 2/15 J plus 14/15 K. We also have our vector F, which is given as a magnitude to be determined on a unit vector in the direction of F, and that is 9 over 11I minus 6 over 11J minus 2 over 11K. Now keep in mind that the component of F that's parallel to AB is found by taking the dot product between the force vector and the unit vector that points in the direction of the axis or the line of action. And so we could write that as our unknown magnitude on UF dotted into UR. Our perpendicular component we would get after the fact as the square root of the difference between F squared and F parallel squared. And we have F parallel squared in terms of F, so we can bring that common magnitude out, and then what we have is the square root of 1 minus UF dot UR quantity squared. So we're trying to solve for F, and we know what the magnitude of F perp should be, so we have an expression for our magnitude, which is the prescribed value of the perpendicular component of F over the square root of 1 minus quantity UF dotted into UR quantity squared. We now have everything we need to solve for F. We can find UF.UR from the two expressions given above, and that is evidently minus 1/3 times 9/11, which would be minus 3 over 11, plus 2/15 times minus 6/11, which turns out to be minus 4 over 55, plus 4/15 times a minus 2/11, which ends up being minus 28 over 165. And if we calculate that out, it ends up being equal to minus 0.515. So our value for F is our required 5 Newton perpendicular force over the square root of 1 minus quantity 0.515 squared, and that gives us a value of 5.834 newtons.